All right, so the third talk is by Giovannini from Michigan. He's going to tell us what gradual typing really means.
So thank you, everyone. And I think it's going to be a little hard to follow up that last talk, but I'll do my best. And so this is joint work with Tingting and my advisor, Max, who's in the audience here. So basically, our work here is about constructing a relational semantics for gradual typing using guarded type theory. And don't worry if any of those terms are kind of unfamiliar. We'll define all of them throughout the talk. And then along the way, we'll also highlight what we view as our key technical achievement of potentially broader interest, which has to do with facilitating compositional reasoning in the step index setting. So just to start, for some background, gradual typing is about mixing dynamic and static typing styles in the same language. And in a gradually typed language, programmers can start writing their code in a dynamic style and then over time migrate to a more static style by adding typing annotations. Now, a key notion in the study of gradual typing is a precision ordering, which is the ability to compare programs based on the relative amount of static typing information that they contain. We can think of this as kind of a syntactic relation on programs where a program M is more static or precise than N if, roughly speaking, M has more typing annotations than N does. And so there are two important metatheoretic properties that we're interested in with gradually typed languages. The first is the ability to use type-based reasoning principles. In other words, the statically typed portions of the code base should validate beta-eta equalities. And the second and perhaps less familiar property, though, is called graduality, which says that when we migrate a program by adding typing annotations, the more precise program should behave the same as the original, except to possibly err where the original program did not, if the types are not compatible with the annotations at runtime. So here, M is more precise than N, and so we expect that M should behave the same as N up to M possibly erring where N doesn't. And so establishing these two properties for gradually typed languages has been the subject of a great deal of work. And so why is this so difficult? Well, there's this kind of combination of different features that have to be modeled in gradual typing semantics. So in particular, any such semantics, first of all, has to be able to model effects because gradually typed languages include divergence and errors. And then second of all, we need to be able to model recursive types because we need to handle dynamic typing. And then, of course, we have to model the relational property of precision that we saw previously. And so in this work, we're going to build on two prior approaches to gradual typing semantics. The first consists of operational models using step index logical relations. And these techniques have been used to model a variety of languages that combine gradual typing with other interesting features. Now, unfortunately, the proofs involve a complicated combination of induction on syntax and tedious manipulation of step indices. And this perhaps wouldn't be so bad if we only had to do it once, but we have to sort of repeat these proofs essentially from scratch for each language we're modeling. And so this lack of a compositional building block kind of presents a significant challenge when we want to develop a reusable meta theory for gradual typing. So to achieve compositionality, New and Licata presented a denotational framework for gradual typing using something called classical domain theory. And by classical domain theory, I'm referring to things like omega CPOs and order theory, et cetera. If you're not familiar with that, that's fine. The point is basically that while this approach has the advantage of being compositional, it's unfortunately limited in a fundamental way in what languages it can model. In particular, because it's based on classical domain theory, it's incapable of scaling to handle languages with highly self-recursive features, such as higher order store. And these features are commonplace in real-world languages, so we would want to be able to model them. So in other words, up to this point, the denotational approach to gradual typing, while it is compositional, it's been limited by what it can express. And so then our goal in this work is to get kind of the best aspects of both of these approaches. We want the compositional nature of denotational semantics and the expressiveness of the step indexed approach. And so a key ingredient in the way we're going to do this is something called guarded type theory, which we can think of as a non-standard foundations where we have axioms that capture the reasoning principles involved in step indexing. So we can think of it as a meta-language in which we can define denotational semantics for programming languages that involve general recursion. Crucially for us, guarded type theory differs from classical domain theory in that it can scale to arbitrarily complex recursive definitions. So what are the new axioms that we get with guarded type theory? Well, first of all, there's this operation later on types. So a value of type later x is intuitively a value of x available one kind of computational step in the future. And then we have this function next where we can turn something available now to be available one step later. And then lastly, and perhaps most importantly, is this idea of guarded recursion. So this says that whenever we have a recursive type equation where the variable x is guarded by a later, we can actually solve it uniquely. And so this is kind of the key, the distillation of the reasoning principles that step indexing gives us as axioms in guarded type theory. Now, the most kind of important thing to remember about guarded type theory for this talk is that it's intentional. And by intentional, I mean like it's sensitive to steps. So the denotation of a term in guarded type theory reflects the computational steps that it takes. And this is in contrast to classical domain theory where the steps taken are not reflected in the denotation. Now, our main result in this work is a denotational semantics for a simple gradually typed language defined in guarded type theory. The language that we model has natural numbers, products, and call-by-value style functions. And the semantics we get out is this partial function from closed terms of type nat to either a natural number or a runtime error. And it's a partial function because the program may not terminate. Now, our semantics satisfies the two key properties we discussed earlier. So first of all, it validates type-based reasoning. That is, if two closed terms of type nat are equivalent according to the theory, equational theory, then they have the same behavior. And then second of all, our semantics validates graduality. So if m and n are closed terms where m is more precise than n syntactically, then semantically either m errs, in which case we don't care what n does, or m and n have the same behavior. So now let's dive into more detail about how we actually define the semantics, and keeping in mind the places where guarded type theory makes things easier and where it kind of introduces challenges. So the first question we should ask is, how are we going to model effectful programs? So the language we're modeling involves errors and computational steps. So the free error domain construction takes a set A and returns a new type, which we write as shown here on the left of the slide. And we define the free error domain on A via a guarded recursion, which was that reasoning principle we introduced earlier. And it's the solution to, the unique solution to this equation shown here. And so an element of the free error domain is then either a returned value of type A, an error, or an element defined later. And this element defined later can be thought of as kind of a thinking or computing element, so that after one time step has passed, we'll be able to access that element. And just kind of for notation, we'll use these three constructors to represent those injections into the sum. Okay, so now let's talk about how we can model dynamic typing. So formally, gradually typed languages have this special type called dyne, written as a question mark, and it represents a statically unknown type. So the language we're modeling, recall, has natural numbers, products, and functions. And so to model dynamic typing, we seek this object D satisfying the equation shown on the slide. Now, we note that D occurs on the left of the arrow in the function case, which means that this equation does not have actually inductive or co-inductive solutions. It has solutions using classical domain theory, but as I said, in this work, we're using guarded type theory rather than classical domain theory. And so if we guard the negative occurrence by placing a later outside of the function case, we can now solve the equation using a combination of least fixed point and guarded recursion. And you can see the paper for more details on how we solve this. The important thing here is that although this use of the later modality gives us a semantics for the dynamic type essentially for free, a program now has to take an observable step whenever it wants to inspect a value of the dynamic type when that value happens to be a function. because it's only available one step later. And so this fact has actually major implications for defining the relational semantics, as we'll see next. And so I guess before we get to the relational semantics, we need to introduce a little bit more about gradual typing. So we've already seen term precision, which models when the types in a program are more precise than another. But of course, there's also an ordering on the types themselves as to when one type is more precise or less or more dynamic than another. And so we call this type precision. And the dynamic type is sort of the top element in this ordering because it is the least precise or most dynamic type. Now, given two types in this relation, we also have casts. So if A is more precise than A prime, we can upcast a term of A to be of the less precise type, and similarly, we can downcast to be the more precise type. For us, the important thing to remember is that casts can take steps in our semantics. This is a result of the intentional nature of our model, because as we saw with Dyn, we used guarded recursion, and there was the later case for functions. So when we downcast from dynamic to a function type, we actually need to wait a step. Now, prior work has shown that the graduality property essentially boils down to the behavior of cast terms. So in particular, there are these 4 key axioms that capture the intended behavior of casts, 2 for upcasts and 2 for downcasts. Now the details aren't really important, but the basic idea is that upcasting should make terms less precise in the ordering and downcasting should make them more precise. Now importantly, the axioms shown here are actually simplified from the original formulation as used in prior work. And it's a concrete benefit of compositional reasoning, a concrete benefit of compositional reasoning allows us to derive the more complicated rules, the original rules, from the ones shown here, rather than needing to prove the complicated ones from scratch in the model, as was done in prior operational approaches. So now let's look at how we might attempt to model type and term precision in our semantics. We'll base the semantics on the prior denotational model of New and Licata, but adapt it to the guarded setting as follows. So first, we'll model our types as sets with a partial ordering relation, representing term precision on values. Terms will then denote monotone functions into the free air domain. And then a type precision relationship between types A and A prime will be modeled as a representable relation between the denoted posets. The precise definition of representability, though, doesn't really matter here. Just note that it's kind of equivalent to this notion of these 4 cast rules that we saw on the previous slide. So it allows us to interpret those. And lastly, we'll model term precision as a logical relation style relationship between the denoted functions. So we map related inputs to related outputs. Now this all seems great, but unfortunately it doesn't work. So the reason basically has to do with the representability requirement here. So in more detail, let's see what goes wrong here. So there's this tension between step insensitivity on the one hand and transitivity on the other, which are both needed properties in our semantics. So we say that a relation is step insensitive if it's oblivious to the steps taken by terms. So we want our relations to have this property because on the one hand, casts can take steps, but on the other hand, representability says that casts have to be related to the identity, but the identity doesn't step, right? So like in this rule here, M on the bottom here is unchanged. There are no steps added, but on the right we downcast, which potentially takes steps. Now, in addition to step insensitivity, we also need transitivity. Transitivity is necessary for us because we want to be able to compose smaller proofs into larger proofs, as we've seen on the previous slide, and that's one of the main goals of our semantics. However, as we show in the paper, there's actually this incompatibility between the two. So we have a no-go theorem showing that unrestricted step insensitivity is incompatible with transitivity. You can't sort of have both in the same relation. So given that transitivity is non-negotiable for our compositional semantics, we give up on step insensitivity. So specifically, we work with a lockstep ordering relation that is transitive, but it's sensitive to steps. So this actually breaks representability because that required step insensitivity. So to fix this, we restore a small amount of step insensitivity in a controlled manner using these special synchronizing terms called perturbations. These are explicitly inserted delay terms that we use to put both sides back into lockstep. So the idea is that the perturbations mimic the stepping behavior of casts, but they're weakly bisimilar to the identity function. That is equivalent to the identity up to or when you ignore steps. And then lastly, we just relax the definition of representability to allow for casts to be in lockstep to perturbations rather than to the identity. And so we can see here the updated rules. And on the side opposite the cast, we allow for there to be a perturbation rather than requiring it to be the identity. And this allows both sides to remain synchronized. So here's how the model looks after making these additions with the new aspects shown in blue. The important takeaway here is just that we've separated term precision into a combination of weak bisimilarity and lockstep reasoning, using the syntactic perturbations as a means to synchronize the terms where needed, which allows for compositional reasoning while still accommodating steps taken by casts. So there's, of course, much more to say in the paper, including details on the guarded type theory, the equation for the dynamic type, and a discussion of the adequacy of our model with respect to graduality. And then in parallel, we formalized most of the construction of our semantics in a variant of Agda called guarded cubical Agda, which extends the type checker with support for primitives of guarded type theory. And some of the highlights are shown here. And we just note that there's a few remaining obligations, including facts about these quasi-representable relations and the syntax to semantics translation. So our next step is to extend this to accommodate languages with more advanced features, such as high-order store or dynamic type tag generation, and prove graduality for alternative cast semantics. And also, it would be interesting to utilize the intentional nature of our model as a kind of cost semantics for the efficiency, to analyze efficiency of different casts semantics. And so, just to recap, we've defined a model for simple gradually typed language using guarded type theory. This combines the compositionality of denotational semantics with expressiveness of step indexing. And we formalized most of this work in guarded cubical Agda. And our key technical achievement here is facilitating compositional reasoning in an intentional setting using a combination of lockstep ordering and explicit synchronizations. So thank you, and happy to take questions.
Oh, okay. I don't have a comment. I actually have a question.
Okay.
Thanks. This is really neat.
Thank you.
I was wondering, are there, since with this intentional extensional property, are there equations that you lose moving from the domain theory to the guarded type theory that you find regrettable, like that you wish you could get back but are currently out of reach?
So I think the interpretation of those cast rules, which had been modeled by this kind of representability condition in the original extensional, classical setting, those we had to sort of make more complicated to build in the fact that terms now can step, or casts can step and keep things in, because we sort of need to keep things in lockstep. So yeah, it would have been much easier had we been able to just use identity function everywhere. But having to keep track of these perturbations was kind of a big part of our semantics.
Is it that the perturbations are just part of the translation from the source language to the cast language, or does a programmer need to think about these at all, or were you able to just kind of automate it away?
No, yeah. This is like the details in the cast calculus, sort of, and yeah. So this would be
Thanks.
Hi, thanks for a really nice talk.
Thank you.
So you defined the semantics of a type as a set, which I assume is a cubical Agda type, plus some extra structure. And so I guess my question is then, what's a term? Is it like a function that does some extra stuff, like respecting the perturbations? Or?
Right. So, good question. Yeah. So the terms are monotone functions because everything has an ordering and now also a bisimilarity relation, which I kind of glanced over. But yeah, every type also has this weak bisimilarity. So the functions are then monotone and bisimilarity preserving. Whether or not they interact with the perturbations, yeah, that's more complicated. But the short answer is no.
Okay, thanks.
The next speaker, please.